Okay, now I will go ahead and get started. So the first thing I'm going to do, you guys, is I'm going to put up a graph of a function. Straight lines aren't my thing today, apparently. Okay, so I'm just going to make up a function. I'm just going to draw it in. It's not going to have, you know, like a set equation or anything like that. I'm just going to draw a picture of a function. Okay, so say this is your function, and we can definitely find the derivative of it, but what I want to show you is what the derivative means on a function. And you probably picked up a little bit of this as we were going. We know the derivative is the slope of a tangent line at any point on the function. So let me pick some points on this function. I'm going to pick one over here, and I'm not even giving specific coordinates, you guys. We're just looking at different points. I want to pick this point here, this point here. Let's pick a point in the middle, and then one over here. So you guys, if I wanted you to find the derivative of the function, you totally could. This would just be like a polynomial function, so it would just be power rule. And then I could have you evaluate that derivative at these points that I've located. Well, what I would find is the slope of a tangent line at each of these points. So at this point over here, you would find a slope of a line that was pretty steep, and it's increasing. You guys, think about lines. If your line is increasing, one thing I know about the slope is that it's positive. So I can guarantee you that this derivative, because it's just the slope of a tangent line, if I evaluate this derivative right here, it's going to be positive. So I'm going to note that the derivative here is positive, and we can see our graph going up. Our graph is increasing, and that is a signal that your derivative is positive. You guys, let's look at this point in the middle. If you calculated the derivative at this point, I'm not very good at drawing tangent lines. But you guys, if you calculated the derivative at this point, you would get the slope of this tangent line. It's going down. You guys, the derivative there at that point, it would be a negative value because that's how you get a negative slope. On the graph, it relates to an area that's decreasing. Over here, you guys, we're going up again, so this one would be positive derivative again. Let's talk about these 2 points. You guys, min and max, you know, things you found in algebra. This is the highest point in its area. This is the lowest point in its area. It's also where things change from increasing to decreasing or vice versa. At this one specific point, if I were to draw the tangent line here, at that instantaneous moment, your tangent line would be horizontal, just for a minute, right? You know, you get up there and it's stuck there for a minute and then it goes back down. So, slope of a horizontal line, guys, is 0. You guys, if you were to calculate the derivative at this point, you would find that it equals 0. And it's the same for this one down here. So, this tangent line, the derivative there would equal 0. So you guys, this is what graphically these derivatives are telling us. Even without knowing what a function looks like. If I said on this side of the graph, the derivative is positive for all points, you would know, you might not know how it's increasing, but you would know it was increasing. The same for a negative derivative, you would know that your graph is going down. Because remember, derivative is just telling us about change. But at any point where your derivative is 0, you're hitting a point like this where things are changing. These are change points. And you guys, I'm going to give it an even more important sounding name. You guys, at that point where things change, we call these critical points. So the first thing we're going to talk about is how to find critical points. All right, so you might wonder why these are important. places where the derivative equals 0. Again, it tells us where the graph is changing direction. I want to know where those places occur. So to find critical points, your first step is to find the derivative. So I'm going to give you a function. I'm not going to graph it because if you have a graph, obviously you can see exactly where all this is happening. But you got an equation and I say, hey, what are the critical points of this function? Where is it changing direction? Well, without having to graph it, you can do it algebraically. First, we're going to find the derivative. And then we're going to set the derivative equal to 0. When I set the derivative equal to 0, I'm going to solve for x. So that's kind of a sub-step here. I am going to set it equal to 0, and I'm going to solve for x. What it's going to give me is these x values right here, where the derivative equals 0. It'll give me x values, not y values, because the critical points are x values. If I wanted to know the y coordinates of these points, once you have the x, it's real easy to sub that in and find the y if you want to know what that is. Usually that's not our main concern anyway. So before we start finding critical points, you guys, I want to make sure that we all understand something. So this derivative over here, we already said it's positive, it's positive. All these points would be positive derivatives until we get here at 0, and then it goes negative. There is no other place where the graph can go from positive to negative without going through 0 first, right? That doesn't make sense unless our graph was broken up or jagged or it had holes in it. The graphs we're going to look at are smooth and continuous. So you know the only time a graph could change from going up to going down is if it goes through one of these critical points. So let's find some critical points. Let's start pretty easy. So you guys, I've got f of x equals 3x squared plus 18x plus 5. Here's my function, and I just say find the critical points. So you say, okay, critical points. That's where the derivative equals 0. So let's find the derivative first. So we get f prime of x. This is an easy
It's
derivative.
cut off a little bit.
Oh. Here, let me move it over. Okay. Thank you for that. You guys, this is an easy derivative. It's just power rule. So I get 6x plus 18. So I found the derivative. Now what do? I set it equal to 0. So when I set it equal to 0, I'm taking this side and writing a 0 here. So I'm going to say 0 equals 6x plus 18. And now I solve for x. This is going to give me the x coordinates of my critical points. So let's subtract 18 on both sides and get negative 18 equals 6x. If I divide both sides by 6, I get just one critical point here. Sometimes we get one, sometimes we get many, depending on what my function started as. But this one just has one, and it occurs at negative 3. So what that's saying is, if I were to graph this function, it would change directions at x equals negative 3. Now, from what I know about quadratic functions where the highest power is squared, I know this is a parabola, so it should make sense that it only changes directions in one place. So this, not necessarily going to graph the whole thing, but it's a parabola. It's going up because the x squared term is positive. So it looks something like this. What I just found is that when x equals negative 3, That has to be the vertex of the parabola. That's where it's changing from down to up. So I found my critical point. What if I want to know the y value here? Let's throw in -3 to your function, and you can find the y value pretty easily. Okay, so you could do f of -3. You get 3 times -3 squared plus 18 times -3 plus 5. So 3 times 9 minus 54 plus 5. All right, so 27 minus 54 is -27 plus 5, and I'll get -22. See, guys, if I ask for the y value at the critical point, here it is. So your critical point occurs at -3, and the value there is -22. Now, because I know a lot about quadratic functions, I knew this was a parabola that was pointing up because this x squared term was positive. I already knew that it was going to go down first, and then it would hit my critical point and then go back up. But when we're looking at functions we don't possibly know a lot about, we have to do a little more work, because it's one thing to say, hey, where's the critical points? You find them, you set it equals 0, whatever, you got them. But beyond that, you guys, I can say this is where it changes directions, but it's harder to say what direction it was going before it got there and then what it changed to, if that makes sense. Especially when we don't know what the graph looks like, but we have ways around that, guys. So I'm going to use this one as an example, even though, yes, I know what direction it's going, but it'll be good to confirm that our method is going to work. Okay, so we found our critical point. My next question for you is going to be for this same function. Find the increasing and decreasing intervals. And again, let's pretend that we don't know what this looks like. So basically, I want to know, where is it going down? Where is it going up? And a lot of our functions are going to have multiple intervals that go up and multiple intervals that go down. So here's what you do. So what did we already do? We found the derivative. We set it equal to 0. We found critical points. Take the x values you found for critical points. Ours just had 1. You guys, so I guess this would be step 3. Put it on a number line. Put your critical point on number line. What we're going to do is called the first derivative test. Now, your number line does not have to have a lot of values on it, you guys. I basically just need to see a number line with -3 in this case. Put -3 in the middle. Here's your critical point. Remember what I said about the graphs and changing directions. They can only change directions at critical points. So it means that everything over here is doing something. It's either increasing or decreasing. There's no changes happening before -3, and there's no changes happening after that. So what we're going to do is we're going to test a value over here, and we're going to test a value over here. Now remember, I don't care what the actual function values are. That doesn't tell me much. What does tell me a lot is what the derivatives at those values are. Because if I test, let's test -4. That's over here. And you guys, you get to pick what you want to test. Something easy, usually. Let's see what happens if I test -4. Now this is called the first derivative test, which means the test that I do will be in the derivative. I don't put -4 into the original function. So let's remember what your derivative was for this function. It was 6x plus 18. So I test -4 in the derivative. Let's see what I get. So I get 6 times -4 plus 18. That's -24 plus 18. I get -6. All right, so I don't care that it's a 6. I care that it's negative. If the derivative at -4 is negative, it means the graph is going down at that point. And because of what I know about the way these functions move, if it's going down here at -4, it's going down for this entire interval. So I tested the value that was on this side of our critical point, and I got that it was negative. I'm just going to put a big minus here. This signifies to me that over here, all these x values that are less than -3 give me a graph that's decreasing. So you guys, let's test a value on the other side. Now, remember, I know what this looks like. I know if this side is going down, that this side would have to be going up, because that's how a parabola works. You don't know how the functions work all the time. So you guys, we test both intervals. We don't ever take it for granted that it's going to alternate. So this is negative, it's going down. Let's test something on the other side of -3. You guys, we can test whatever we want over here. I'm going to use 0. 0's over here somewhere, isn't it? You guys, if 0 is in your interval, I would definitely use that to test. It's so easy, right? So let's test 0. Remember, we're testing in the first derivative. So put in 0 for this derivative here. You'll get 6 times 0 plus 18. And I get positive 18. It's positive at 0, which means I know that it's positive for this entire interval over here. Remember, because this is the only point that it could possibly change. So find increasing and decreasing intervals. Here's how you're going to write your answer. You're going to list all increasing intervals. All of our intervals are in terms of x only. Notice I didn't find the y value at -4. I didn't find the y value at 0 because it really doesn't matter. Unless I specifically ask for it, you won't even find the y value at the critical point because this is all about x's. So increasing interval in terms of x, you guys, it looks like it goes from -infinity all the way up to -3. That's where it's increasing on the x values. So remember how to use interval notation. You guys, interval notation, remember it looks like an ordered pair, but it's really left endpoint to right endpoint, and then it stops. So our left endpoint is -infinity. When it goes on forever, we just say -infinity. And then it comes all the way up to -3. That's where it stops this increasing interval. And you guys, they get parentheses. So interval notation, again, I don't think we've used it in here. You have two choices for how you group these together. So you can have a parenthesis, which is an open-ended interval. It means that our interval stops here at -3, but it does not include that value. If I had a bracket, so maybe I chose to bracket an endpoint, that would mean it stops here and that endpoint is included. So if you want to include your endpoint, you bracket it. If you don't, you leave it as a parenthesis. You guys, when we're talking increasing and decreasing intervals, we never bracket. We never actually include that -3 in our interval. So you guys, this is the increasing interval from x equals -infinity all the way up to this point at -3. If you have more than one increasing interval in your answer, like sometimes we will have more than one, you can either separate them with a comma if you want, or you can use a union symbol. So this is another way to say you have more than one interval. So let's say we had two intervals that were increasing. I could say, here's an increasing interval and also whatever that other interval would be. So it unions them, which is saying this and this, basically. You guys will have to let me know what MathLab likes. I would assume they probably like the union, but that you probably could use a comma also. They've been pretty lenient, in my opinion. So decreasing interval. Oh, guys, I did this wrong. I'm not looking at the problem as I write these. What did I do wrong?
Increasing and decreasing backwards.
Yeah, I increase and decrease backwards. I started with increasing. My goal was to start with decreasing. So remember our problem, because it was negative here, we're actually decreasing in this interval. We're not increasing. I wanted to start with decreasing, but I didn't write that. So sorry. You guys, this interval was decreasing because it was negative when we tested a value. All right, so we did the decreasing interval. Let's do the increasing interval. So increasing intervals are going to occur when the value you test is positive in the derivative. So it's everything else over here, right? Starting at -3 and then going on to positive infinity. So my interval would look like -3 to infinity. And again, no brackets. We never bracket anything on these intervals. So expect to answer, like be able to list critical points and be able to list increasing and decreasing intervals. Let's do them. Actually, before we do another one, I don't know that I want to, guys. I don't want to do another one because they're just going to get more difficult, and our attendance today is so low, and I don't want to have to teach this again. So I am not going to do another one. I'll put homework up if you want to start practicing. There are going to be some more difficult questions. Not that you can't do them. I mean, the steps are the same no matter what. But there are going to be some questions where solving for the critical points, so after you set it equal to 0, it gets harder, i.e. the factoring practice that we did last time. You're going to have to use that. But again, we'll do that in class too on Monday. Yes?
What's your next homework?
You do have
The 11.8.
11
The 20th.
on Sunday?
Yeah.
Okay.
We had nothing to do yesterday, right, on Thursday?
No, we didn't learn anything new on Thursday. So you guys, this homework this week is only 11.8.
Okay, perfect.
And then we'll get this on to the next homework. So not a big deal, but you know, I encourage you to start it if you don't have anything better to do. And then we'll continue with this next time.
And it's like one of the like the ones that have like multiple questions in each one.
Something like, I haven't finished it yet.
So it's like probably 30 or 40 actually.
All right, guys, so I am signing off. I will see everybody on Monday, but on Zoom.
Like, one we have like multiple questions.